So you might ask, why is cofactor expansion even important? And well, it's important because it gives us another method for finding the inverse of non-singular matrices. And so when we take a look at the determinant, we have to consider that when we are doing this operation, we have an actual theorem that says if we sum the products of elements of any row or column times the corresponding cofactors of any other row or column, then we get zero. And this is really interesting because when we look at what is called the adjoint, and in linear algebra there are a couple meanings of adjoint, but in this case we're just going to refer to it as a matrix where the ith and jth entry is the cofactor transpose. So it's basically a square matrix of the transpose of its cofactor matrix. So if you have a matrix and this matrix determinant is not zero, then we can say that the inverse is equivalent to multiplying the adjoint of A times 1 over the determinant of A. And we can see that right here in this definition of the corollary. And so using this corollary, what we want to do is find the inverse of A if it exists, such that A is this matrix right here. And we're going to be using this definition above. So to do this, we're going to just follow the instructions. We want to find the inverse of A. So first we need to find the determinant of A. And the determinant of A can be defined as, and we can also write it like this, -3, 4. These almost absolute value looking bars indicate that it is a determinant. And the way that we calculate this is 4 times 3. We already know how to do this for 2 by 2s, plus, it's actually minus, and I'll show you why, -3 times 2. And so this is going to come out to 12 plus 6. And this equals 18, and 18 does not equal 0. So we've satisfied this first part. This, if A is a square matrix such that the determinant of A is not 0, boom, we've just satisfied that. And so now to find the adjoint, what we'd like to do, and we denote the adjoint as this. A, with the entries, is equal to, and in the last video I said, oh, this is because it's 0, but in reality, it's because if you've ever taken calculus or you know anything about alternating series, we have this series where the ith and jth index are being added right here, boop, as exponents. And what happens here is 1 plus 1. And what happens here is we're going to actually have something kind of cool happen. So this is going to be -1 to the second power, and this is going to be positive, right? So we can just put a positive. We know our answer is going to be positive because, just over off on the side here, I'm going to do, for those of us who don't really know how this works, -1 squared is equal to 1 because we have 1 times -1 equals 1. And so this tells us that our series at this point, or our entry at this particular index, is positive. And if we recall from the determinants, what we can remember is something like this. I'm going to just put this on the side. For n equals 3, say we have a 3 by 3, right? For n equals 3, we have the entries of the determinant being, and you might remember this from like the cross product, even in Calc 3, where you'd have to use something like this for the most part. And what we have is the determinant ended up being this pattern where we have this. And so n equals 4 would just be a continuation of this, oddly enough. And it would just be positive, negative, positive, negative, negative, positive, negative, positive. They are almost orthogonal in a way. And it just repeats. And you can pretty much take this all the way as long as you want. And so having understood this, now we know why this thing is alternating. Okay? And that's how we get the positive and negative signs. It's kind of interesting that they alternate in this way. All right, so let's get rid of that real quick, and we're going to just stick with this. And so now that you can recall some of the determinant, to finish calculating the adjoint, we have times 4. And the reason why we do that is because we take the entry that is not in the first row or the first column. And the only one that suits this or fits this is 4. So what we're going to do is say this is times 4, the entry not in the columnar or the row. And this is just going to be 4, positive 4. And so this is the adjoint. This is one of the cofactors in solving for the adjoint. And we could do the same with the second one. So the second, we could just say is this. Let's get rid. Okay, so we have the second and we have the first. And the one that we are going to be using, we have the first column and the second row. And so the only one that we don't have is this. And this is going to always be this entry on the outside. We can always say that this is going to be now -3 because this is the entry that we're looking at. And we have -1. And this is just a good way to remember, okay, well, I don't have to do this positive and negative thing. I don't have to recall exactly where I am. I can just plug it in according to the index. And this is going to be 1 plus 2. And this is going to give me -1 to the third, and this is going to be a negative number times -3. And what we can say is -1 times -3 is equal to 3. And this is another entry that we're going to be using. And to finish this up, we're going to do this. So now I've just found the other two based on the size of the matrix. It's a 2 by 2. So that means we have to find 4 cofactors. And so what we can say now is that the adjoint, here's the big moment, right? The adjoint of A, you could denote it like this, is actually just the matrix of all of these cofactors. So solving for these, I've just made some notes on the side. I've just taken these and I've just put them right here so they're easier to find. And then I've put them into this matrix, and that is the adjoint of A. And to find the inverse, which is what we really want, what we want to do now is we want to just look at the definition, which is the inverse is equal to 1 over the determinant of A, and I'm just going to denote it like this for now, times the adjoint of A. We're going to say that the inverse is equal to, well, we already know this. This is 1 over 18 times the adjoint, which is 4, -2, 3, and 3. And this is how we can find the inverse. And the inverse is just going to be 2/9. After, obviously, we just use this as a scalar. -1/9, 1/6, and 1/6. Using this definition, we've now just found the inverse.